Hi, my name is Fabian Seiler, and today I want to talk about the paper Efficient Image Processing via Memristive-based Approximate In-Memory Computing, which was accepted at the transaction of Computer-Aided Design for Integrated Circuits and System. The main methodology for this work was to combine two computing paradigms that are currently emerging. The first is In-Memory Computing and the second Approximate Computing. The main methodology of our work was to present 4 approximated adder algorithms. For this we used the series-serial topology, as you can see here, which consists of 2 computational areas that are independent to each other, enabling a parallelization compared to other topologies. Both of these computational areas can be connected to the carry memristors, so the C and the C-in, and also the work memristors, which are used to store intermediate results. We utilize the approximation that sum is approximately equal to the inverse of the carry-out if we assume the equations of a full adder. Here you can see an example algorithm where first the work memristors are reset, afterwards different stateful logic steps are calculated, which results in the carry memristor being overwritten with the results of the carry-out. And the A memristor is overwritten with the results of the sum. In total, we developed 4 approximated adder algorithms, where the Carnot diagram for the carry-out is presented here, where you can see that for each algorithm, one carry-out placement is wrong, and which is also propagated to the sum. So let's go to the simulations and experiments we actually done. We utilized SPICE simulations to evaluate the waveforms of all different input combinations for all of the 4 algorithms. We calculated the energy consumption by averaging over the different input combinations. We also did an output validation where we checked if the resulting output states actually corresponds to the theoretical calculations. We also did extensive R-on and R-off deviation experiments, which represent the resistive states of the memristor. As you can see, up to 30%, plus minus 30% deviation still leads to correct results. This was done with a tool called Atomic, which you can find here and will be explained in another video. Now let's go to the circuit level comparison, where compared to the exact semi-serial adders, up to 38% less energy and up to 35% fewer steps are required, which is quite an achievement compared to the already efficient semi-serial adder topology. Compared to state-of-the-art serial approximated adder, so in the serial topology, up to 30% less energy and 54% fewer steps are required at the same approximation degree. The downside of using the semi-serial topology compared to the serial one is that 3 more memristors and additional CMOS switches are required. We also achieve a better accuracy with 2 of our algorithms compared to the state-of-the-art. As you can see here, the algorithms represented in the semi-serial topology achieve quite a gains in terms of latency and also in terms of energy consumption. So we're more efficient in both these regards if we're considering the same approximation degrees. If we now look at the application level, we evaluated 3 image processing applications. We used image processing since it is an error-resilient application and is actually really useful for approximate computing. We calculated the total number of total energy and the total number of steps that can be reduced when our approximated approach is used. Here you can see the energy consumption for the 3 applications with an approximation degree of 5 out of 8. And as you can see, our first algorithm, being the most efficient one, up to 15 millijoule of energy can be saved for a single image. The same is true in the number of steps, where our first algorithm is also the fastest algorithm, and up to 36 million steps can be saved. That was all for now. Thank you for watching and have a nice day.